Hi, so I was requested by one of the teachers to make a quick video of what is happening in our most recent section 2.2, specifically just that introductory piece to proof. So I know some people have been absent or just maybe got a little bit lost in there. So I thought I would take a moment to show a couple of quick examples of some proofs. I hope this video doesn't turn out to be overly lengthy, but I hope it's still helpful regardless. So for starters, when we do a proof, I want to go ahead and click share here. A proof right here is an argument that uses statements and logic to arrive at a conclusion. And so that's what we're doing is we're going to be making a really, really organized logical argument to take pieces that we know, facts and information that we know to try to draw a simple conclusion. And those facts can be just like definitions of words. Like if we use the word midpoint, we know it's the point smack dab in the middle of a segment. Or if we use the word supplementary, we would know it's two angles that add up to 180. But we also have simple things like this, where if you added something to both sides and that was beneficial to you, then the justification or the reason behind that logic would be addition property, which allows you to do that. Or subtraction property allows you to subtract the same thing from both sides. And so that tends to be one of the kinds of justifications that we use on these problems. So again, what I'll start with is a pretty easy little idea. And so usually in proof, at least at the beginning stages where we are right now, we haven't done anything really crazy yet. We usually have these problems set in a given and prove story. Okay, so given something, let's prove something. And so let's say we had given that 1/3 of x plus 7 is 11. Let's prove that x must in fact be 12. Now, this would be an example of the kind of thing that we might want to prove. Now, again, I'm going to lay out a logical set of arguments to start with this statement of fact and arrive at this conclusion down here. So the first thing that we would normally do is choose to write the original statement. And I always have to have some kind of a justification. I have a statement over here. I have a justification over here. And my justification for this being true is that I told you it was true, that that was the given information. Now, step 2 is we're going to do a variety of different things. Now, what I would probably want to do is take 7 away from both sides. So if we had this statement and we took 7 away from the left side and the right side, we could do that by the subtraction property. Because the subtraction property of equality, hopefully I can fit that in here, tells me I can subtract the same thing from both sides. So that's fairly simple logic. Now, that does mean, though, that these two 7s are going to cancel out, and I end up with 1/3 of x being exactly 4. And that's true because what I just did is I simplified what I had. Right? I simplified the mathematics that was in front of me. Now I'm getting closer, but now what I would want to do is I would want to probably multiply both sides by 3. So that's what I'm going to do in this next step. Is if we are right here and we chose to multiply both sides by 3, we would call that the multiplication property. Let's see if we got where we wanted to go. So now I would notice that, again, by simplifying, because that's all I would do last, is that 3 times 4 is in fact 12, and these cancel out. That's why I did it, and that gives me x equals 12. And we should notice at this moment right now, we are good to go because I started with the given and I was able to come up with a logical set of steps that brought me to what I was trying to prove. That's how proofs are. Now, in algebra, it's a little more straightforward sometimes than it is in geometry. Geometry is a little more of an advanced concept, at least at this level, than Algebra 1. And so I thought I would do, this is problem 42. This is actually the lecture, or just kind of what we worked on in class, number 42. And this is the first one we would do in more of a geometric setting. Now, one of the problems here is that this problem doesn't have a diagram, and I always feel like in geometry we should have a diagram. And it says M is somewhere between A and B. That's all this says. Now, it never actually said anything else, but it says, oh, I want to show that I drew that kind of poorly, that in fact AM and MB would have to be exactly the same. I want to show that it's a midpoint. So my given information is that M is between A and B. That's the first piece that was given. The second piece is that AM is exactly 1/2 of AB. And what I'd like to prove is that M is the midpoint. Now, we were talking earlier in the week about what we call conditional statements, if-then statements. So you're going to notice that this is the hypothesis right here. This front half is the hypothesis. That's my given. The conclusion is what I'm trying to prove, which makes sense. The conclusion of an essay is at the end. What we want to prove is right at the end. So here's what we're going to do. We always start our proof with just that given information. So let's start there. That M is between A and B, and that AM is 1/2 of AB. Now, I will tell you, if you watch online and you watch how other people prove, sometimes they would choose to make this one statement 1 and this one statement 2, and they'd have given and another given. I usually just wrap them together. Everybody has their own style. Now, one thing that I do is I look at a proof like a journey. And when I'm all done, I want to land at this place right here. And what would it take to show that they are equal is I would want to show that AM is the same as AB. And that's where we're going to go. So here we go. The first thing I'm going to use is something that is called the segment addition postulate. Now, the segment addition postulate was used in one of our first quizzes of the year. I'm looking for this diagram. See, on this quiz that we had that segment C lies on BD, and we said one side was 51, this was 22, and you guys were supposed to do this to come up with the number 73, that the left side plus the right side is the whole thing. Well, that's what I'm going to do in our story. That if I were to take AB, that would be AM plus MB. The segment addition postulate allows me to do that. Now, here comes the important thing. This is just sort of one of those things that tends to happen in these problems. There's a piece of the given information that I haven't utilized yet, and it's right here that AM is exactly 1/2 of AB. So if I could go to this thing right here and replace AM with 1/2 AB, that's going to do something very, very nice for me. And I'm going to call that substitution property. The substitution property allows me to take something out and put something that's equal in its place. And this says AM is identical to 1/2 AB. So there we go. I've got AB equals 1/2 AB plus MB. Now, with that being stated, I could, and this is where I'm going to do it a little different than I did that last one, because sometimes I try to go a little shorter, a little quicker proof. I'm going to choose to take 1/2 of an AB away from both sides, because what I'd really, really like to do is just get all of the ABs on the same side together. And I think that makes sense. If this was an X and that was a 1/2 X, you'd want to put them together. So let's see, step 4, an AB take away 1/2 of an AB is 1/2 of an AB. And over here, these cancel, and I'm left with MB, and I just subtracted from both sides. So I'm going to call that subtraction property. I could do that in 2 steps because we kind of also simplified, if you think about it. We didn't only subtract, we also made that look easier. But here we go. This is the big part that I want to make sure that I make it really, really clear. AM is half of AB. See that right there? But it says MB is also half of AB. So if half of AB could be written as AM, but if half of AB could also be represented as MB, then that tells me that AM and MB are in fact identical statements, right? Because they're both equal to half AB. That's again substitution. I took something out and I put something in its place. I took this half AB and I replaced it with AM. And that leads me to my very last statement. If AM right here is in fact perfectly the same as MB, that means that M must be smack dab in the middle. If that's 8 and that's 8, that puts it dead center. And so I am now going to be able to conclude that M is the midpoint of AB. And this is a really super important little thing to know, is that whenever you use words like this, that are kind of not your average everyday language, typically what follows them up is the definition of that word. The reason I am allowed to call M the midpoint is this right here perfectly matches what the definition of a midpoint happens to be. And I have finished my story because I got to the end and I got to exactly the place that I said I wanted to the proof. Okay. Now, number 43 is a very, very similar problem to number 42, but it doesn't talk about segments, it talks about angles. So the first thing challenge-wise, we need to go ahead and figure out what my given is, what I'm trying to prove, and maybe come up with a reasonable diagram that makes sense. Given EG is the angle bisector of angle DEF. Okay, so I'm just writing out the given information. I want to prove it's the conclusion is what we're trying to prove, that the measure of angle DEF is equal to twice the measure of angle DEG. So, well, let's see. It says EG is a ray and it bisects, well, let's start with DEF because it's mentioning some angle DEF, which makes E the vertex, DEF, and E has to be the vertex because the vertex is always in the middle. And it says EG, well, it has to go through E, and it's supposed to bisect this angle, so it's going to come through here somewhere like that. So EG is bisecting it. Okay, so here we go. Let's see what we can do. Let's start off with our given information. And my given information is that EG is the angle bisector of angle DEF. Okay. Now, I'm actually going to rewind us back to our previous problem. And again, this isn't always the case, but it's a good way to go. So what I'm going to say is that I know that DEF, which is the entire angle right here, could be broken up as the top angle DEG plus the bottom angle GEF. Now, notice when we did this over here, I broke a segment into 2 pieces, and we called that the segment addition postulate. This, of course, is then called the angle addition postulate. Now, that actually did 2 things for me. Number one is it got something to just start it off. And the other thing that's actually kind of important is, remember, my journey is I want to get to this number, this idea being on the left side and something else being on the right side. And what I want you to notice is I already have on the left side exactly the statement that I want, but you're going to see something else. I want DEG, and I already have DEG sitting right there. So that's kind of interesting. I already have the building blocks. It's already sitting very similar to what I want to see. So step number 3, again, if there's ever a weird phrase that's, again, not common verbs, not common language that you use all day, every day, angle bisector is not one of those words. We're going to talk about what the definition of angle bisector is. Because what a bisector does is it splits things into two, that's bisect means cut. Angle bisectors cut perfectly into equal pieces. Well, that would mean that angle DEG is perfectly the same as the measure of angle GEF. Those two things are perfectly the same. Now, keep in mind, I've got these two little statements, and when I look up here, I'm getting very, very close to what I want, but I don't really want GEF in the statement. Notice if we look up here, I didn't have GEF in that statement. But right here, I know that GEF is exactly the same as DEG. So I could take this GEF right here, and I could put a DEG in that place, and that's going to make it say more like what I want. So step number 4 is that the measure of DEF equals the measure of DEG, because that's what I already had. But instead of writing this one, I'm going to substitute something that's equivalent to right here. Now, again, keep in mind, we still have what we wanted, right? And now all of a sudden, we have what we wanted both times. And that's getting now very close to what we wanted. I wanted a DEF and I wanted 2 of these, and that's actually exactly what I have is I have 2 of those. So the only thing I need left to do is to simplify my statement. Because instead of saying DEG plus DEG, I'm going to say I have 2 of those DEGs, which of course is the same as DEF. And that finishes my proof because you'll notice I got where I was wanting. It's a nice logical argument that is fairly easy to understand, especially if you have a little bit of background in geometry. And that will finish my first video on proof. All right, I hope that helped. Bye-bye now.